Hello, I will walk you through an exercise where we use the Matrices formalism to set up a model and simulate it. Let me bring up a slide. Here's our overview of the Matrices formalism, which, however, you would have to study using the materials, and a picture of Carl Adam Petrie on the left, after which this formalism is named. So what we are going to do is we're going to take a simple example of one reaction and apply to it the formalism such that we get the input and output matrix first, then derive reaction and stoichiometry matrix, analyze the model by checking T and P invariants, and finally do a very quick simulation of that model. So our simple reaction is one that uses hydrogen ions, it's acidic pH, hydrogen peroxide, and NADH in its reduced form under the catalysis of peroxidase, yielding 2 molecules of water and 1 of NAD+. A reaction involved in the destruction of potentially toxic levels of hydrogen peroxides in cells. So to implement this, let's create a new MATLAB script. Let's save it under some name, say POD for peroxidase, and start our model by setting up the input and output vectors. So in order to remind us of what our species involved in that model are supposed to be, I'll just copy and paste here the names of them. We're not going to use it further, but just to have it in our script and to remind us of the order in which they appear. So we need to first formulate input and output vector for this reaction. And we formulate it by assigning it to a variable. So in each case we'll have a vector in square brackets, and the first vector will summarize the substrates only. So what do we have? So we have a molecule of hydrogen ion, one of hydrogen peroxide, one of NAD+, but of course none of the products. And for the output vector we'll have again square brackets. We'll have none of the substrates as a result of the reaction, and we'll get 2 molecules of water and 1 molecule of NADH. So that completes input and output. From this, we can formulate the reaction matrix A as their difference. So we take the output minus the input, and that will be the reaction matrix A. And at the same time, we can, of course, directly write down the stoichiometry matrix, which is nothing but the reaction matrix transposition here, done by using the apostrophe or single quote. This output we can suppress because the same numbers will be in both matrices, just in a different form. So the result here, if I just make that visible, the input vector, the output vector, and the resulting reaction matrix, which is a single row vector in our case of only one reaction. Let us now check invariants, and we know, or we can find out, that invariants are obtainable from the either reaction or stoichiometry matrix. So first of all, look at the P invariant, and we'll get this as the null space of the reaction matrix using the argument R for rational output. That's in case we have small numbers. So we can execute this code, and we can see that there are a couple of columns, means a couple of invariants. So let us remember the interpretation. What is a P invariant? A P invariant is supposed to show us conserved moieties. So which combinations of particle numbers will be unchanged? under simulating the reaction network. So the way to read it is to go down column-wise and say whenever there's a 0 you ignore it, but in this case where you have now integers, you need to consider those particle numbers. So in this case the first is our hydrogen ion. Take the particle number of hydrogen ions times -1 negatively and add to it the particle number of species number 2, which is hydrogen peroxide. And the sum of the two, one's negative, one positive, should not change during the course of the reaction. Which is clear because they will both in a reaction reduce by 1. So if you take one negative and one positive and add them 1, their sum will not change at all. If we look at the third column, we can also see that if you want to have this conserved moiety, it would be hydrogen plus water. And to calculate it, you take 2 times the number of hydrogen ions and you add to it the number of water molecules here, and that number will also remain constant throughout the reaction, whatever the number of reactions that have taken place is. So 4 conserved moieties, 4 P invariants in this very simple model. If we now continue and check our T invariants, and we'll do that with just the same similar code. It's the null space obtained this time from the stoichiometry matrix. Again, rational basis with argument R. We can see the output in the command window, and the output is nothing. T vector, the T invariant, is empty, so it means in this special case there isn't any T invariance. There isn't a set of reactions that leaves particle numbers unchanged. Of course, it's trivial here because there is only one reaction. Particle numbers will always change because it's irreversible, but it will be different in large reaction networks. That completes our analysis. So let's now proceed and do as a final part a simulation of that model. How do we do that? First of all, we need to define how quick is that reaction, how many reactions take place per unit of time. So we can formulate a vector u, which in this case is simple because we have only one reaction, and we just arbitrarily assume, let's say there's per time unit, there are 2 reactions on average that take place. So that's our number of reactions per time unit. And the corresponding change per time unit will then be whatever the stoichiometry matrix tells us is happening times that vector u. So that will be the net change during one time unit. It means we will lose from the substrates 2 of each of the substrates. We'll gain 4 molecules of water and we'll gain 2 of the NAD+. So before we can actually do a simulation, what we need to do is to define a species vector. So let's do that. Let's define our species vector, and the species vector we call it M, and it will be also in square brackets, and we need to produce an initial number for 5 species. So let's arbitrarily assume we have 10 of each of the substrates. Then it would be 10, 10, and 10. Note that I separate them by semicolon because we need species as a column vector. And let's assume there's none of the products initially present. So we have 0 and 0 for the 2 products. So having formulated an initial species vector, we can now calculate the number of particles at each of the time points into the future for an arbitrary length of time. So how do we do that? We take that initial species number and we add to it the net change per time unit. So if the net change per time unit is S times U, as we have formulated it, then M plus S times U gives us the simulation output. Let's just run a simulation. Right, so that's the output after one time unit. From 10, 10, 10 we come to 8, 8, 8 in substrates, and from 0 we go to 4 molecules of water and go to 2 molecules of NAD plus as products. That's basically it now. The only thing that we need to consider is what if we have a larger amount of time, not just one time unit. So if we formulate a period of time as, say, 5 time units, then the way to update this model would be just to multiply this with the time period. So the update would be initial vector plus times the time times s times u. So what happens if we let the model run 5 time units, or we wait 5 time units? The result is given here in the command window. We have consumed all of the substrate molecules and we have gained 20 molecules of water and 10 of NAD+. So this concludes our simulation, and just as a warning in the end, MATLAB will not stop at 0 particle units. It will move forward into negative numbers if you just let it go. You can check it yourself. So if you want the reaction to stop when species of the substrates are 0, then you need to put in additional code, for example, conditional statements.